Electromagnetic radiation is all around us all the time. It brings color to our eyes, powers medical imaging, and even food preparation. But what is it, and how is it used? Let's discuss it, fellow Philomaths. Have you ever wondered how X-ray machines work? Or how a microwave oven works? While it may not seem like it, these machines utilize electromagnetic radiation to function. The same thing that brings visible light to our eyes. Visible light is one of many types of electromagnetic radiation, which we'll talk about later. Electromagnetic radiation, or EMR, is the propagation of electromagnetic waves through space. While that may sound confusing, we'll break it down into simpler terms. Let's walk through it. In electromagnetic radiation, there are two synchronized fields oscillating or moving back and forth, perpendicular or intersecting at 90 degrees to each other, the electric field and the magnetic field. These oscillations can be viewed as waves. The varying frequency, or how fast the wave oscillates, of these waves gives them unique characteristics. We'll talk about this later. In these waves, the wavelength is equal to the crest-to-crest or trough-to-trough distance. Frequency is inversely related to the wavelength by the following equation: F equals V over lambda, where F is equal to frequency, V is equal to the speed of light, c, and lambda is equal to the wavelength. An important concept we must understand is that EMR can have properties of both a wave and a particle. This idea comes from the wave-particle duality concept in quantum mechanics, where EMR is shown to have properties of a wave and a particle. The particle of EMR is the photon. We can think of photons as packets of EMR, and they carry energy according to the Planck-Einstein relation. The Planck-Einstein relation shows that E is equal to h times V, where E is equal to photon energy, h is equal to Planck's constant, V is equal to the frequency in hertz. Photon energy is commonly measured in both electron volts, eV, and joules, J. You see, as a wave's wavelength decreases, its frequency increases. Looking back at the Planck-Einstein relation, we can see that as a photon's frequency or wavelength changes, the photon's energy changes. The varying photon energy gives us a wide variety of properties. This leads us to the introduction of the electromagnetic spectrum. As you can see, the electromagnetic spectrum is divided into several sections with specific ranges of frequency and wavelength. Radio waves, for example, take up a large portion of the electromagnetic spectrum, while the visible light portion is small. These sections have unique properties. For example, gamma rays carry a significant amount of energy, enough to ionize an atom or molecule. On the opposite end of the spectrum, radio waves carry a very small amount of energy and can have very large wavelengths. Because of their changing properties, different types of EMR are used in different ways. Let's begin this section with a brief understanding of atomic structure. In an atom, there is a core, called a nucleus, composed of protons and neutrons. In an ordinary atom, the number of protons is equal to the number of electrons. Electrons are bound to the nucleus and have a negative charge, while the proton has a positive charge. The electron has different energy levels it can be in. In order to reach or jump to a higher energy level, an electron must absorb a specific amount of energy. If an electron wants to reach or jump to a lower energy level, it must release a specific amount of energy. This process is known as an atomic electron transition. Sure, electrons can be at different energy levels, but how do they get there? One of the ways an atomic electron transition occurs is through electromagnetic radiation. If an electron is exposed to a photon carrying the right amount of energy, it will absorb the photon and jump to a higher energy level. In contrast, for an electron to jump to a lower energy level, it must release the excess energy. That energy is released in the form of electromagnetic radiation. With a basic understanding of what EMR is, let's now discuss a few origins of visible light. The device you're watching this on probably uses LEDs to power its display, but how do they work? In an LED, there are two semiconductors made from a special material that can emit light efficiently. On one side, there is an N-type semiconductor, which has many free electrons. On the other side, there is a P-type semiconductor, which contains an excess of electron holes. When we pass an electrical current through the system, excited or high energy level electrons jump to fill the electron hole on the other side, releasing excess energy as electromagnetic radiation to lower its energy level. This process is known as electroluminescence. In an incandescent light bulb, an electrical current is passed through a filament, typically tungsten. While the electrons are passing through the filament begins to heat. Once the filament reaches a certain temperature, it emits electromagnetic radiation as a result of heat. This process is known as incandescence. Incandescent bulbs are relatively inefficient sources of light, though, as less than 5% of the input energy is transformed into visible light. Now let's discuss the light source with which you are most familiar, the sun. Stars, our sun included, are powered by the process of nuclear fusion. Nuclear fusion occurs when atoms are fused together to form another atom. This is no easy task though. Protons have a positive charge, so two protons repel each other, meaning a great amount of energy is required to fuse them together. In the core of the sun, however, there is an immense amount of heat and pressure, which allows for nuclear fusion reactions to occur. Now that we have an idea of what EMR is and where it comes from, we can discuss a few of its applications. Let's begin this section with a device you're probably familiar with, the microwave oven. What happens when you place that delicious leftover pizza in a microwave oven? Well, the microwave oven is utilizing the properties of microwaves, a form of electromagnetic radiation, to heat your food. A microwave oven contains a device called a magnetron, and when powered, this device converts large amounts of electrical energy into electromagnetic radiation in the microwave portion of the spectrum. When these microwaves reach your food, they begin vibrating the molecules on or near the surface of the food. These vibrations create thermal energy, which the molecules radiate to other molecules in the food, heating it. So next time you heat up some food in your microwave oven, remember that you are utilizing the power of electromagnetic radiation. X-rays have a number of uses. Most notably, though, is in projectional radiography, or simply an X-ray machine. X-ray machines allow doctors to examine the inner structure of the human body. But how? To start, an X-ray generator releases X-rays towards its target, your broken arm, for example. Some of the X-rays struggle to pass through the denser parts of your body, like your bones, whereas X-rays have no problem passing through your flesh. Behind the target lies an X-ray detector, a device that intercepts these X-rays to create an image. If X-rays make it to the detector, they darken the area where they land, but the parts that aren't struck by the X-rays appear white. X-ray machines provide medical professionals with quick, sometimes life-saving information that they wouldn't have rapid access to otherwise. Electromagnetic radiation is fascinating, and while I've only listed 2 examples of its applications, electromagnetic radiation has limitless potential in the realm of innovation and creativity. All it takes is curiosity and passion to discover something new, traits which the alluring nature of science can instill in you. Thank you for your time, and continue to pursue the path of a Philomath. Goodbye.